Space is a breathtaking void of profound beauty and silence. But that emptiness is an illusion, hiding dangers that are both invisible and terrifying. For anyone who dreams of the stars, understanding these hidden threats is not just fascinating, it is essential for our survival. We are about to unveil 25 hidden dangers in space, a countdown of cosmic threats that range from microscopic particles that can shred your DNA to colossal explosions capable of sterilizing entire planets. This knowledge is your shield, the crucial first step in preparing humanity for its greatest adventures. What unseen force could wipe out our technology in an instant? What silent traveler from the depths of the galaxy poses a permanent risk to any astronaut? The answers reveal a universe that is far from peaceful. What do you believe is the most underestimated danger waiting for us in the dark? The silent vacuum is saturated with an invisible rain. This is cosmic radiation, the first and perhaps most pervasive danger on our list. It is not a single source, but a constant, torrential downpour of atomic fragments. These particles are the shrapnel from colossal stellar explosions, accelerated to nearly the speed of light across unimaginable distances. Our own sun contributes its own stormy weather, blasting out solar particles that add to this relentless hail. Think of your body not as solid, but as a collection of trillions of tiny, intricate structures. Now imagine a subatomic bullet, smaller than an atom, tearing through that delicate architecture. Each impact can slice through DNA strands, causing damage that your body's repair mechanisms struggle to fix. The consequences are not a distant fear. Astronauts report seeing flashes of light behind their closed eyelids, a terrifying sign that these particles are piercing through their eyes and interacting directly with their optic nerves. The long-term health risks are starkly clear: a significantly elevated lifetime risk of cancer and potential for degenerative damage to the brain and central nervous system. This radiation does not just target flesh and blood. It is a silent saboteur of the machines we rely on for survival. A single high-energy particle can flip a critical bit in a computer's memory, causing a spacecraft system to glitch or fail at the worst possible moment. We have already mapped some of the most intense zones of this radiation. The Van Allen belts surrounding Earth are donut-shaped regions of trapped particles, a radioactive barrier that missions must quickly traverse. And the surface of Mars, a future destination for human explorers, lacks a global magnetic field and has a thin atmosphere, offering little protection from the full brunt of cosmic radiation. For any long-duration mission beyond the safety of Earth's magnetic shield, to the Moon or to the red plains of Mars, this invisible killer is the primary problem we must solve. How can we possibly build a shelter that protects us from a form of rain that passes through solid metal? The answer may lie not in thicker walls, but in smarter, more ingenious forms of defense. Our own star, the Sun, is not the gentle bringer of light it appears to be. It is a seething cauldron of incandescent plasma, capable of unleashing fits of cosmic violence that make cosmic radiation seem like a steady drizzle. This is the Sun's wrath, the second great danger on our list: solar flares and coronal mass ejections. These are two different yet often related explosions of terrifying power. A solar flare is a sudden, intense flash. Think of it as a bomb going off on the Sun's surface, releasing a tremendous burst of radiation across the electromagnetic spectrum, from radio waves to powerful X-rays. This flash of energy travels at the speed of light, reaching Earth in just over 8 minutes. But sometimes, a more sinister event follows. A coronal mass ejection is a slower, far more massive eruption. The sun belches out a billion-ton cloud of magnetically charged plasma, a solar hurricane that billows outward at millions of miles per hour. While the radiation from a flare arrives in minutes, this colossal cloud takes hours or days to cross the void. It is this cloud, this coronal mass ejection, that holds the most catastrophic potential for a world like ours. If one were to score a direct hit on Earth today, the consequences would be almost unimaginable. The first wave of destruction would be invisible. The intense magnetic forces carried by the plasma would induce enormous electrical currents in anything long and metallic on our planet. Power lines would act as giant antennas, overloading transformers and causing permanent, widespread damage. The entire global power grid could collapse, leading to a blackout that could last for months or even years. Simultaneously, our fleet of satellites would be fried. Communication, GPS, weather forecasting, and global finance would simply cease to function. For astronauts caught outside the protective bubble of Earth's magnetic field, the event would be lethal. Without the massive shielding of a planet between them and the storm, they would be bombarded with radiation doses high enough to cause severe sickness or death within hours. We are not speaking in theoretical terms. History provides a chilling precedent. In 1859, a colossal coronal mass ejection, now known as the Carrington event, slammed into Earth. Telegraph systems, the advanced technology of the age, spectacularly failed. Operators received severe shocks, telegraph paper caught fire, and the northern lights were seen as far south as the Caribbean. The world of 1859, with its simple technology, could weather such a storm. Our deeply interconnected, electricity-dependent civilization of today would be brought to its knees. A modern-day Carrington event would be a global catastrophe of unprecedented scale. The question is not if another one will hit us, but when. While the sun's fury poses a planet-wide threat, a more intimate and immediate danger silently zips through the void. This is the realm of micrometeoroids and space debris, the third hidden danger on our list. Imagine a tiny chip of paint. It weighs almost nothing in your hand. But in the vacuum of space, this same fleck is traveling at over 17,000 miles per hour. At that velocity, it carries the kinetic energy of a bowling ball thrown at full force. It becomes high-speed shrapnel, a bullet with no sound. The International Space Station bears the scars of this relentless assault. One of its most famous windows, part of the cupola module that offers a breathtaking view of Earth, has a small chip in its thick fused silica glass. It was struck by a fragment of space debris, perhaps a tiny flake of metal or paint, leaving a permanent crater as a stark reminder of the vulnerability that surrounds our astronauts. This is not just about cosmetic damage. A direct hit on a critical system, a coolant pipe or a pressure hull, could lead to a catastrophic depressurization. Solar panels, essential for power, can be gradually eroded and torn apart by these microscopic impacts. And this threat is not just natural. We have filled our own backyard with a cloud of our own making. Decades of spaceflight have left a swirling graveyard of discarded rocket bodies, dead satellites, and countless fragments from explosions and collisions. This is space junk, a field of orbiting shrapnel that grows with every mission. The real terror lies in a theoretical domino effect known as Kessler Syndrome. Picture a single collision between two large objects, say an old satellite and a spent rocket stage. That impact does not just create two pieces of debris. It creates thousands of new fragments, each one a new bullet. Those fragments then increase the probability of further collisions, which in turn create even more debris. This cascade could eventually reach a tipping point, where low Earth orbit becomes so densely packed with fast-moving junk that it is effectively impassable. Satellites would be shredded, the space station would be uninhabitable, and any rocket attempting to launch would be flying through a cosmic minefield. We would be trapped on our own planet, sealed off by a shell of our own discarded technology. The silence of space is already being filled with the whispers of a coming storm. Beyond the silent rain of radiation and the hailstorm of debris lies a danger defined by brutal extremes. Space is a realm of fire and ice, a vacuum where temperature is not a gentle gradient but a violent switch. An object floating in direct sunlight can be heated to over 250 degrees Fahrenheit, hot enough to boil water and scorch metal. Then, as it rotates into shadow, that same object can plunge to 250 degrees below zero in a matter of minutes. This fourth danger, extreme temperature swings, is a constant engineering war against the void. Every spacecraft, every satellite, and every spacesuit is a fragile bubble of stability fighting an unforgiving environment. The side facing the sun bakes, while the side in shadow freezes. Without a sophisticated system to manage this, the results are catastrophic. Sensitive electronics would overheat and melt in the sunlight, then become brittle and shatter in the deep cold. For an astronaut on a spacewalk, a failure in the liquid cooling and ventilation system woven into their suit would be a death sentence. In the sunlight, their body would rapidly overheat, leading to fatal heat stroke as their own metabolism and the sun's relentless energy cook them from the inside. In the shadow, with the suit's heaters offline, the cold of space would siphon away their body heat with terrifying speed, inducing a lethal hypothermia. The only defense is a complex, relentless ballet of technology. Spacecraft are coated in reflective white blankets or polished gold foil to deflect solar radiation. They use networks of pipes carrying coolant, like a circulatory system, to carry excess heat from the hot side to the cold side, where it can be radiated away into the void. Louvers open and close like automated blinds, regulating the internal temperature with meticulous precision. A single failure in this delicate balance, a punctured coolant line or a stuck louver, can doom an entire mission and everyone aboard. This is the paradox of surviving in space, a place where you can simultaneously freeze and burn, all within the span of a single orbit. How you build a home in an environment that is actively trying to shatter you with cold and melt you with fire. The brutal extremes of fire and ice are not the only way the void attacks a fragile body. There is a far more immediate and visceral horror waiting just beyond the thin shell of a spacecraft or suit. The vacuum of space is a danger defined not by force, but by absence. It is a near-perfect emptiness, a pressure so low it defies our earthly experience. A common misconception is that the vacuum sucks. The reality is more violent. It is about explosive expansion. Your body and the air inside your spacecraft exists at a comfortable pressure. The vacuum outside is essentially zero. When a barrier between these two states is breached, the high-pressure gas does not get pulled out. It violently expands outward into the emptiness, ripping everything with it in a furious rush to equalize. This is explosive decompression, the fifth and most cinematic danger on our list. For an unprotected human, the consequences are swift and gruesome. The first and most critical effect is the immediate lack of oxygen, a condition called hypoxia. You would not have time to hold your breath. In fact, trying to do so would be disastrous, as the pressure difference would rupture your lungs. Instead, the air in your lungs is forcibly expelled. Within 10 to 15 seconds, the oxygen in your blood stops reaching your brain, and you lose consciousness. This rapid knockout is a small mercy, as it spares you the full experience of what follows. Without the pressure of our atmosphere to keep them in check, the fluids in your body begin to vaporize. This is ebullition, the boiling of bodily fluids. It does not happen because space is hot, but because the boiling point of liquids plummets in a vacuum. Saliva on your tongue would instantly fizz. The moisture in your eyes, your skin, and your soft tissues would start to bubble and swell. Your body would balloon to perhaps twice its normal size, though your tough skin would likely prevent a true explosion. Hollywood often gets this wrong, depicting people freezing solid or their eyes popping out in an instant. The cold of space would eventually claim you, but it would take much longer than the lack of air. The historical record provides chilling, real-world glimpses. In 1966, a NASA test subject was accidentally exposed to a near vacuum when his pressure suit leaked in a vacuum chamber. He passed out in about 12 seconds, but later reported that the last thing he felt was the saliva on his tongue boiling before he lost consciousness. He survived because the chamber was repressurized within 30 seconds. This event, and a handful of others like it, have given us a grim but clear understanding of our limits. The vacuum is not a monster that actively hunts you. It is an indifferent emptiness that your body is simply not built to endure. Your very biology is tuned for a world of pressure and air, a world that vanishes in an instant the moment a seal is broken. The vacuum outside is a physical threat, but the emptiness within a spacecraft can be just as perilous. Human minds are not designed for the profound isolation of deep space, creating a sixth danger that is entirely psychological. This goes far beyond simple homesickness. On a journey to Mars or beyond, astronauts would be farther from Earth than any humans in history, a tiny speck in an infinite black sea. The knowledge that rescue is impossible, that you are utterly on your own for months or years, applies a unique and crushing psychological pressure. We have seen glimpses of this in extreme environments on Earth. Crews overwintering in Antarctic stations, sealed away from the world for months of perpetual darkness, report intense strains. Submarine crews living in cramped, windowless tubes for long patrols face similar challenges. But in space, these effects are magnified 1,000-fold by the sheer distance and the alien environment. One documented phenomenon is a specific neurosis called asthenization. It is not just feeling tired. It is a gradual wearing down of the psyche, marked by severe irritability, insomnia, and a deep emotional withdrawal. A crew member might become hypersensitive to the sounds of their companions, or fixate on minor annoyances until they become sources of deep resentment. In a sealed can where you cannot step outside for a breath of fresh air, these festering conflicts can threaten the entire mission's success. Compounding this is the paradoxical nature of the view. Gazing at the beautiful, fragile Earth from orbit can induce a powerful cognitive shift known as the overview effect, a feeling of universal connection and peace. But on a long voyage, that beautiful blue marble shrinks to a mere star, then to a faint point of light, and finally vanishes from sight entirely. The psychological tether to home is severed. You are no longer in orbit around the world. You are truly, deeply alone in the cosmos. The mind can struggle to find its footing in such immensity. How do you maintain your mental stability when your entire world is a few metal rooms? Your only companions a handful of people you cannot escape. and outside your window lies an endless, silent void that offers no comfort. The greatest challenge may not be building a ship that can survive the journey, but building a mind that can endure it. The mental isolation of a long journey is terrifying, but another alien threat could be hiding on the very worlds we seek to explore. This is the seventh hidden danger, the silent risk of alien microbes, and the critical need for planetary protection. It sounds like the plot of a science fiction thriller, but scientists treat this concern with absolute seriousness. The danger flows in two directions: a biological cross-contamination that could have irreversible consequences. First, there is the fear of what we might bring back to Earth. Imagine an astronaut returning from Mars with soil samples clinging to their suit. Unknowingly, they carry a microscopic stowaway, a Martian microorganism that has survived the journey. Earth's entire biosphere has evolved for billions of years, developing defenses against known pathogens. An alien microbe would be completely unknown. Our immune systems would have no reference, no antibodies to fight it. It might not even be intentionally harmful, but its mere biological processes could be toxic to our biochemistry, triggering allergic reactions or fatal illnesses on a global scale. This is the essence of the backward contamination risk, the terrifying scenario of an Andromeda strain. The second, more immediate danger is the one we pose to other worlds. This is forward contamination. We have sent our robots and will one day send our people to places like Mars or Jupiter's moon Europa, worlds that might harbor their own simple, fragile life in subsurface oceans or soil. Our spacecraft, no matter how well cleaned, are covered in hardy Earth microbes. These tiny life forms, bacteria like Deinococcus radiodurans, can survive the vacuum of space and intense radiation. If they are carried to a place like Mars and find a trace of water, they could thrive, spreading across the planet. The result would be a scientific and ethical catastrophe. We might arrive to find Mars, only to realize we are not discovering native life, but the descendants of our own contamination. We would have erased the very evidence we sought, forever losing the chance to answer one of humanity's oldest questions: are we alone in the universe? This is why space agencies enforce strict planetary protection protocols, treating spacecraft like surgical instruments that must be sterilized before touching a new world. The greatest danger might not be what waits for us out there, but what we accidentally bring with us. The invisible threat of alien microbes forces us to look outward, but a far more personal danger attacks the human body from within. Even inside the safe, pressurized hull of a spacecraft, your own biology begins to turn against you. The eighth danger is the betrayal of gravity's absence, a physiological war fought in the silent peace of orbit. In microgravity, the very definition of up and down vanishes, and your body, evolved over millions of years to fight Earth's constant pull, begins to unravel. Without that force to work against, your muscles start to waste away at an alarming rate. The large muscles in your legs and back, your calves and your quadriceps, are the first to suffer, as the body decides they are no longer essential for survival. Astronauts must strap themselves into treadmills and resistance machines for 2 hours of intense exercise every single day, just to slow the decay. But the most insidious loss happens where you cannot see it, deep inside your skeleton. Your bones, no longer bearing weight, stop regenerating. The cells that build new bone go quiet, while the cells that break it down continue their work unabated. The result is a devastating loss of bone density, at a rate of 1 to 2% every single month. Compare that to an elderly woman with osteoporosis on Earth, who might lose 1 to 2% in an entire year. After a long-duration mission, an astronaut's skeleton can resemble that of someone decades older, becoming fragile and prone to fractures upon their return to a world with gravity. At the same time, a strange and unsettling shift occurs with your bodily fluids. On Earth, gravity pulls your blood and other fluids down into your legs and lower body. In space, that pull is gone. Fluids drift upward, pooling in your chest and head. This is why astronauts often have puffy faces and prominent neck veins in their videos from the space station. This constant pressure in the skull is now believed to be the cause of a serious, long-term problem. Permanent vision changes for many astronauts. The pressure flattens the backs of their eyeballs and inflames their optic nerves, leading to a farsightedness that can persist for years after they come home. This is not mere discomfort. It is a sign of profound systemic stress affecting the brain and the central nervous system. The immune system also seems to become confused and sluggish, less able to fight off infections that would be trivial on Earth. The cardiovascular system, no longer working against gravity to pump blood upward, weakens, making the return to Earth's pull a dizzying, exhausting ordeal. We have developed countermeasures for a 6-month stay in orbit. But what about a 3-year journey to Mars? The cumulative damage could be crippling. And this is only one side of the cosmic coin. If we ever discover a world with stronger gravity than our own, a super-Earth, the challenge would be reversed. The simple act of standing would feel like carrying another person on your shoulders. Every step would be a monumental effort. Your heart would struggle to pump blood to your brain against the immense pull, and your bones would be under a constant, crushing strain. Our bodies are fine-tuned for one specific gravity well. Stepping out of it, whether into weightlessness or into a heavier embrace, reveals a terrifying truth. We are not just visitors in space. We are prisoners of our own planet's gentle tug. Even as our bodies adapt to the void, our connection to home grows strained by an unbreakable law of physics. The speed of light is both a universal constant and a profound limitation, creating a silent barrier that may be the greatest test of human ingenuity. This is the 9th danger, communication lag, and the terrifying blackout zones of deep space. That instantaneous link we take for granted on Earth simply does not exist beyond our atmosphere. A signal racing at the speed of light takes time to travel the vast distances between worlds. A conversation with astronauts on the Moon is merely an awkward pause, with a delay of about 2.5 seconds each way. But for a crew on Mars, that delay stretches to an agonizing 20 minutes, and at its farthest point, over 40. A simple question from mission control would take 20 minutes to reach the red planet. The crew's answer would not begin its journey back for another 20 minutes. A single exchange of information would consume the better part of an hour. Now, imagine a crisis unfolding aboard the spacecraft. An alarm blares, warning of a sudden pressure leak or a fire in an electrical panel. On Earth, mission control sees the same alarm, but they are watching events that happened 20 minutes ago. By the time they analyze the data and formulate a response, 40 minutes have passed. The emergency on the ship has already been resolved, or it has ended in tragedy. The crew is utterly, completely on their own. There can be no real-time troubleshooting, no expert guidance from the best minds on the planet. Every critical decision, from a course correction to a medical emergency, must be made autonomously by the astronauts, with the full knowledge that any mistake could be their last. This profound isolation is punctuated by periods of total silence known as communication blackouts. During a high-stakes maneuver like an orbital insertion or a planetary landing, the spacecraft might need to fire its engines in a way that blocks its own antenna. Or it might dip behind a planet, with the entire bulk of the world shielding it from Earth's transmissions. For those tense, critical minutes, the crew is cut off from any contact whatsoever. They are a single voice in an immense, silent cathedral, with no one to hear their calls for help or their cries of success. This is not a temporary inconvenience. It is a fundamental redesign of human exploration, forcing us to send not just astronauts, but entire, self-sufficient communities into the dark. Can a small group of people, millions of miles from home, possess the collective knowledge, skill, and nerve to survive when the only voices they can hear are their own? The silence of a communication blackout is a stark reminder of our isolation, but another invisible shield protects us every moment on Earth. Our planet's magnetic field is a colossal, dynamic force field, a bubble of magnetic energy generated by the churning of molten iron in Earth's core. This magnetosphere is our first and most vital line of defense against the sun's unrelenting fury. It acts like a cosmic shield, bending and deflecting the vast majority of the sun's charged particles, the very same ones that create solar storms and contribute to cosmic radiation. Without it, our atmosphere would be slowly but surely stripped away by the solar wind, leaving our world as barren and exposed as Mars. The red planet stands as a haunting example of a world that lost its global magnetic field billions of years ago. Its core cooled and solidified, the planetary dynamo shut down, and its protective shield vanished. The result is a surface that is ruthlessly bombarded by solar and cosmic radiation, a key reason why Mars appears so lifeless today. For future colonists, this magnetic deficiency is not a theoretical concern. It is a daily, accumulated threat. Living on Mars would mean living under an open sky of radiation, with only the thin Martian atmosphere and the soil beneath their feet offering minimal protection. Every walk on the surface, every moment spent in a habitat, would add to their lifetime radiation dose. The increased risks are severe, a dramatically higher chance of developing cancer, and the potential for cumulative genetic damage that could affect future generations. Building a settlement on Mars is not just an architectural challenge, it is a radiological one. How do you create a safe, long-term home on a world where the very environment is actively hostile to life? The answer may require us to become architects of our own magnetic shields, generating artificial magnetospheres to protect the pioneers who dare to live on a world without one. Even the emptiest reaches of space are not truly empty. High above our heads, a whisper of Earth's atmosphere remains, a ghostly presence that exerts a constant, invisible pull. This is the 11th danger, the slow and inevitable grip of orbital decay and atmospheric drag. For any object in low Earth orbit, this is a relentless battle against physics. While we think of space as a perfect vacuum, the extreme upper atmosphere still contains a few stray molecules. A satellite or the International Space Station, hurtling at 17,000 miles per hour, constantly collides with these tiny particles. Each impact is minuscule, but together they create a force of friction, a drag that ever so slightly slows the spacecraft down. And in the delicate ballet of orbital mechanics, speed is everything. The station is in a constant state of falling around the Earth, its forward velocity perfectly balancing the pull of gravity. Reduce that speed, and the balance is broken. Gravity's pull becomes stronger, and the station's orbit begins to decay, dropping it into an even denser part of the atmosphere, where the drag increases, creating a feedback loop of decay. This is why the International Space Station requires a regular reboost. Every few months, a visiting cargo spacecraft must fire its engines, pushing the entire massive complex back up to its proper altitude. Without these carefully orchestrated boosts, the station would begin a slow, spiraling descent. Its solar panels would start to vibrate and strain in the thickening air. The delicate science experiments would become inoperable, and eventually, the descent would become a plunge. This is the ultimate fate of all objects in low Earth orbit that lack the fuel or ability to fight back. The uncontrolled re-entry is a terrifying spectacle. As the object slices deeper into the atmosphere, friction heats it to thousands of degrees, transforming it into a fireball. Smaller objects vaporize completely in this incandescent shower, but larger pieces, like heavy titanium fuel tanks or dense engine components, can survive the inferno and slam into the Earth's surface. We are protected by the fact that most of our planet is ocean, but the risk is never zero. An uncontrolled re-entry is a cosmic game of roulette, with debris scattering over a path hundreds of miles long. This invisible drag is a reminder that nothing in orbit is permanent. Every satellite we launch, every piece of hardware we leave behind, is ultimately living on borrowed time, caught between the void above and the restless atmosphere below. That invisible drag is the prelude to a far greater disaster, a chain reaction that could seal our path to the stars. We have already littered our celestial backyard with a cloud of shrapnel, but the true nightmare is when this debris begins to create itself. This is the Kessler Syndrome, a cascading catastrophe that stands as the 12th hidden danger in space. Picture a single, catastrophic accident in orbit, a collision between a dead satellite and a discarded rocket body. The impact does not simply create two large pieces of junk. It shatters them into thousands of new fragments, a cloud of high-speed shrapnel expanding outward. Each new piece, from a bolt to a shard of solar panel, now becomes a bullet in its own right, traveling at orbital velocities of over 17 miles per hour. The density of objects in that orbital highway has now increased. This raises the statistical probability of another collision. When that next collision occurs, it too creates thousands more fragments. This is the cascade, a self-sustaining chain reaction where each crash begets the next, exponentially multiplying the amount of lethal debris. The tipping point is the moment when the process becomes unstoppable, even if we never launched another rocket. The debris field would feed on itself, growing denser and more violent with every passing year. The consequence is an orbital region, most critically low Earth orbit, becoming an impenetrable and permanent minefield. Satellites providing essential services would be shredded within months. The International Space Station would be punctured beyond repair, forcing its abandonment. Any new spacecraft attempting to launch would be flying into a blizzard of high-speed projectiles, with a near certain chance of being destroyed. We would be trapped on our own planet, our access to space severed for generations, perhaps even for centuries. The silent infrastructure we depend on every day would vanish in a flash. Global positioning systems that guide our travel and power our financial networks would go dark. Weather satellites that give us early warning of hurricanes and typhoons would fall silent. Worldwide communications, from television broadcasts to international phone calls, would disintegrate. This is not a distant science fiction plot. We have already witnessed previews of this nightmare. In 2009, a defunct Russian satellite collided with an active American communications satellite, creating over 2,000 large, trackable pieces of debris and countless smaller fragments that still threaten other assets today. In 2007, China deliberately destroyed one of its own weather satellites in an anti-satellite missile test, a single act that created the largest field of space debris in history, with over 3,000 trackable objects. Each of these events pushed us measurably closer to the brink of Kessler Syndrome. The question is no longer if such a cascade could happen, but when we will cross that invisible line of no return. How do we clean up a mess that is moving faster than a rifle bullet and spans an entire planet? Even the most desolate landscapes on Earth offer a sliver of hospitality, but the surfaces of our neighboring worlds are realms of pure antagonism. Venus is a vision of hell, a world where the very air is a weapon. The atmospheric pressure on its surface is a crushing 90 times greater than what we experience on Earth. It is the equivalent of being submerged a full kilometer beneath the ocean's surface, a force that would instantly implode any submarine we have ever built. The temperature soars to a staggering 800 degrees Fahrenheit, hot enough to soften lead and ensure that no complex machinery could operate for more than a few minutes before melting into a useless puddle. And the clouds are not made of water vapor, but of corrosive sulfuric acid, a perpetual biting rain that never reaches the ground, instead evaporating in the infernal heat below. A human standing there would be simultaneously crushed, incinerated, and dissolved. It is not merely an uninhabitable planet. It is a world that seems to actively reject the very concept of life. Then there is Mars, a world that at first glance seems almost familiar with its rusty deserts and polar ice caps, but its soil hides a silent chemical threat. The Martian regolith is rich in perchlorate salts, compounds that are toxic to the human thyroid gland and can cause severe health problems with prolonged exposure. For any future colonists, this dust will be an inescapable part of daily life. It will cling to spacesuits, it will be tracked into airlocks and habitats, and its fine, abrasive particles will threaten to clog machinery and infiltrate seals. Managing this toxic dust will be a constant, exhausting battle against a world that poisons you by degrees. Meanwhile, on the distant moon Titan, a different kind of hostility awaits. The temperature plummets to 290 degrees below zero, so cold that water ice becomes as hard as granite. Here, rivers and lakes are not filled with water, but with liquid methane and ethane, hydrocarbons that flow like petrol across an alien landscape. A probe sent to this world would not need to withstand blistering heat, but a cold so profound that standard electronics would shatter and fail. Each of these worlds presents a unique and brutal puzzle for survival. How do you build a settlement in an atmosphere that acts like a corrosive, superheated fluid? How do you farm in soil that is actively poisonous? The environments of our solar system are not just empty stages waiting for our arrival. They are active participants, armed with chemical, thermal, and physical weapons designed to destroy any visitor from Earth. The solar storms from our own star are just the beginning of a deeper radiation threat. Lurking in the vast gulfs between galaxies are projectiles of unimaginable power. This is the 14th hidden danger, the relentless assault of galactic cosmic rays. These are not mere protons from the sun. Galactic cosmic rays are the atomic nuclei of heavier elements, atoms of iron and even uranium that have been stripped of their electrons and accelerated to within a fraction of light speed by the most violent events in the cosmos. They are the shrapnel from supernova explosions and the debris flung from the edges of ravenous black holes. Their energy dwarfs that of typical solar radiation, making them the ultimate penetrating radiation. A single iron nucleus from a galactic cosmic ray carries the force of a major league fastball, condensed into a subatomic bullet. When one of these particles slams into the hull of a spacecraft, it does not just stop. It creates a secondary shower of radiation, a cascade of even more particles that sprays inward, amplifying the damage. This makes them exceptionally difficult to shield against. LEED, the traditional barrier against radiation on Earth, can actually make the problem worse by generating more of this secondary shrapnel upon impact. The only real defense is mass, immense thicknesses of water, plastic, or specialized composites. But the weight of such shielding makes it currently impractical for long-duration missions. The health risk is severe and cumulative. Each of these heavy ions can tear through cells, causing complex clusters of DNA damage that are far more difficult for the body to repair than the damage from solar particles. The result is a significantly elevated lifetime risk of developing cancer, a silent, statistical threat that builds with every day spent in deep space. There is a cruel irony in our solar system's natural defenses. The sun's own magnetic field, which billows out to form the heliosphere, actually helps to deflect some of these galactic cosmic rays. But the sun's activity is not constant. It follows an 11-year cycle of high and low activity. During solar minimum, when sunspots are few and solar storms are rare, the sun's magnetic field weakens. This allows more of these powerful galactic cosmic rays to flood into our solar system. The quietest periods for the sun are, paradoxically, the most dangerous times for astronauts to be traveling through interplanetary space. The radiation environment becomes significantly more hostile. This creates a terrible dilemma for mission planners. Do you launch during solar maximum and risk encountering a catastrophic solar storm? Or do you launch during solar minimum and subject the crew to a higher, constant dose of the most penetrating radiation known to science? It is a choice between a sudden, violent catastrophe and a slow, invisible poisoning. How do you plan a journey where the very space between worlds becomes more toxic depending on the mood of our star? That invisible shield of atmospheric drag becomes a wall of fire when you need it most. Returning home from orbit is a controlled fall through a fiery gauntlet, a 15-minute ride through hell that is the 15th hidden danger, the perils of re-entry. A spacecraft in orbit is traveling at over 17,000 miles per hour, a speed that must be almost entirely scrubbed away before it can land safely. There are no gentle brakes in the vacuum of space. The only way to slow down is to use the Earth's own atmosphere as a shield, plunging into it and trading that incredible speed for intense, brutal heat. This heat is not generated by simple friction, as many believe. It is caused by a phenomenon called compression. The spacecraft is moving so fast that it cannot push the air molecules aside. Instead, it slams into them, compressing the air directly in front of it into an incandescent plasma. This creates a sheath of superheated gas that can reach temperatures of 300 degrees Fahrenheit, hotter than the surface of most stars. The spacecraft is literally setting the air on fire around itself. The only thing standing between the astronauts and this inferno is the heat shield, a carefully designed ablative plate on the underside of the vehicle. It is engineered to slowly char and burn away, a sacrificial layer that carries the extreme heat with it as it vaporizes. A single flaw in this shield, a crack or a missing tile, can be a death sentence. The precision required for this maneuver is absolute. The spacecraft must hit the atmosphere at exactly the right angle. If the angle is too shallow, the craft will not bite into the atmosphere deeply enough. It will skip off the top, like a stone skimming across a pond, and be flung back out into the void on an unstoppable trajectory into deep space, with no hope of return. If the angle is too steep, the deceleration forces become too extreme, potentially crushing the astronauts, and the heat generated will quickly overwhelm and destroy the vehicle. There is only one narrow corridor, a keyhole in the sky, that leads to a safe landing. The tragic reality of this danger was etched into history on the first day of February 2003. The Space Shuttle Columbia was returning from a successful 16-day mission. As it began its re-entry, the superheated plasma found a weakness. A piece of foam insulation had broken off during launch and had struck the leading edge of the shuttle's left wing, damaging the crucial thermal protection system. The crew aboard had no idea. They went through their re-entry checklist as the plasma, over 300 degrees, seeped into the wing's aluminum structure. Inside mission control, sensors began to fail. Then communication was lost. To the world watching, the shuttle simply disintegrated in the sky, a trail of debris scattering across the southern United States. The Columbia disaster is a permanent, sobering reminder that the journey is not over until you are safely on the ground. For those few terrifying minutes, you are riding a meteor of your own making, trusting your life to a shield that must burn to save you. The fire of re-entry is a danger we can see and feel, but the greatest threats to the cosmos itself are completely invisible. We have mapped the stars and the galaxies, yet we must confront a humbling truth. Everything we can see, every star, every planet, every speck of cosmic dust, accounts for less than 5% of the universe. The rest is a profound mystery, a darkness filled with forces we do not understand. This brings us to the 16th danger, the unseen architects of reality, dark matter and dark energy. Dark matter is the hidden skeleton of the cosmos. We cannot see it, touch it, or interact with it through light, but we know it is there because of its immense gravitational pull. It is the invisible hand that holds galaxies together. Without the gravitational glue of dark matter, the incredible speed at which stars orbit the center of a galaxy would send them flying off into the void. Our own Milky Way is embedded in a vast, spherical halo of this mysterious substance. While dark matter itself does not reach out and grab you, its uneven distribution could theoretically create regions of space that are more hazardous than others. Imagine a future where our spacecraft travel between stars. If they were to pass through an unexpected, dense knot of dark matter, the intensified gravitational forces could violently wrench the ship from its course or place unbearable stress on its structure. The path between stars might not be the empty highway we imagine, but a landscape shaped by invisible, gravitational mountains and valleys. But dark matter is only half of the mystery. The other, far more strange and powerful force is dark energy. This is not a force that holds things together, but one that pushes them apart. In the late 1990s, astronomers made a shocking discovery. The expansion of the universe is not slowing down due to gravity, as everyone had assumed. It is accelerating. Something is actively stretching the fabric of space itself, and that something is what we call dark energy. This is a danger on a scale that dwarfs all others, a threat not to a single mission or a single world, but to the ultimate fate of everything. If dark energy continues to dominate and strengthen over billions of years, it could lead to a theoretical end of the universe known as the Big Rip. In this scenario, the accelerating expansion first tears apart galaxy clusters, then individual galaxies. As the force grows stronger, it would rip stars from their solar systems. and planets from their stars. In the final moments, the very atoms that make up all matter would be torn asunder, shredded by the relentless expansion of space itself. The cosmos would end not in fire or ice, but in a silent, irreversible isolation. We are living in a universe dominated by entities we cannot perceive, forces that control our destiny on the grandest scale. How do you plan for a future where the very space between atoms could one day become a weapon? The architects of dark energy and dark matter shape the cosmos, but other wanderers patrol the darkness with a more direct form of menace. Drifting through the interstellar void are the orphans of cosmic chaos, rogue planets. These are entire worlds that were violently ejected from their nascent solar systems by gravitational encounters with sibling planets, sent careening into the abyss. They travel in perpetual night, without a star to warm them, their surfaces frozen to temperatures near absolute zero. The true danger is not the planet itself, but its silent, unseen gravity. If one of these dark wanderers were to make a close pass through our solar system, its gravitational pull would be like a cannonball rolling through a carefully arranged set of billiard balls. It could destabilize the delicate orbital dance of the planets, tugging asteroids from the stable belt and sending them on a collision course with the inner worlds, including our own. It could nudge the orbits of the giant planets, creating a ripple effect of instability that would chaotically rearrange our entire cosmic neighborhood over millions of years. Even more elusive are the ultimate gravitational traps, black holes. We often picture the supermassive giants at the centers of galaxies, but there is a more intimate threat. Stellar mass black holes, the remnants of collapsed giant stars, could be littered throughout the galaxy, invisible against the blackness of space. And there is the theoretical possibility of primordial black holes, tiny relics from the Big Bang itself that could be drifting unseen. A spacecraft on an interstellar voyage would have no warning. There would be no visible sign, only a subtle change in trajectory as the ship crossed the event horizon of even a small black hole. The gravitational tides would be so extreme that they would spaghettify the ship and its crew, stretching them into a stream of atoms before they were swallowed by the singularity. The greatest fear is that one of these gravitational ghosts could be lurking in our own cosmic backyard, a silent predator waiting in the dark for an unsuspecting traveler. How many of these unseen wanderers are passing through our solar system right now, completely undetected by our telescopes? The void is not empty. It is haunted by the gravitational echoes of things that should not be there. These gravitational ghosts are not the only invisible killers in the dark. A flash of light from the edge of the visible universe can carry more energy than our sun will emit in its entire 10 billion year lifetime. This is the 18th danger, the gamma ray burst, the single most powerful explosion known to exist since the Big Bang itself. These events are the final death cries of the most massive stars in the cosmos. When a star many times heavier than our sun exhausts its fuel, its core collapses not into a neutron star, but directly into a black hole. In that cataclysmic instant, twin jets of concentrated energy are blasted from its poles at nearly the speed of light. These are not wide, expanding bubbles of energy like a supernova. They are focused beams, tighter and more intense than any laser, slicing across the galaxy like cosmic blowtorches. Alternatively, when two ultra-dense neutron stars spiral into each other and merge, they too can unleash a similar, devastating beam of pure gamma radiation. If one of these beams were to be pointed directly at Earth from within our own galaxy, the consequences would be an extinction-level event unparalleled in our planet's history. The first wave of destruction would be the radiation itself. For just a few seconds to a few minutes, the sky would glow with a light brighter than 1,000 suns, all pouring out in the invisible, high-energy gamma ray part of the spectrum. This intense blast would instantly shred our planet's protective ozone layer, the shield that protects all life from the sun's harmful ultraviolet rays. With that shield gone, the surface of the Earth would be bathed in a lethal dose of ultraviolet radiation from our own sun. Land-based life would suffer catastrophic radiation burns. The base of the food chain, phytoplankton in the oceans, would be devastated, collapsing ecosystems worldwide. But the horror does not end there. The gamma rays would rip apart nitrogen and oxygen molecules in the upper atmosphere, reassembling them into nitric oxide, a compound that would act like a corrosive smog, further destroying the ozone and blotting out the sun, potentially triggering a rapid global ice age. The planet would be simultaneously irradiated, burned, and frozen. Life on Earth would be effectively sterilized. The most sobering part of this threat is its suddenness. Because these beams travel at the speed of light, the first warning we would have would be the arrival of the radiation itself. There is no way to see it coming. We would only know it was happening when the sky itself began to kill us. We are protected only by the sheer improbability of such an event. For a gamma ray burst to wipe us out, it must be relatively close, within a few thousand light years, and its deadly beam must be aimed with perfect precision at our tiny, pale blue dot in an ocean of stars. It is the ultimate cosmic lottery, a game we are playing every moment without even knowing the dice are being thrown. That profound silence from the cosmos is not just empty, it is profoundly unsettling. Where are all the other civilizations we expected to find? This question is the heart of the Fermi paradox, and it points to our 19th hidden danger, a threat that is not a physical force but a philosophical and existential one. The universe is ancient and vast, with billions of planets that could support life. The math suggests the galaxy should be teeming with intelligent species, their radio signals and megastructures evident across the light years. Yet when we listen, we hear only silence. This great silence implies something is terribly wrong. One terrifying explanation is the concept of a great filter. This is a hypothetical barrier, a challenge or a developmental stage so difficult that virtually no civilization in the universe can survive it. The filter acts as a cosmic sieve, wiping out intelligent life before it can become a multi-planet, star-faring species. The chilling question for us is the location of this filter. Is it in our past, perhaps the emergence of life itself, or the jump from single cell to complex multicellular organisms, was the nearly impossible step? If that is true, then we are the rare, lucky ones who made it through, and the galaxy is empty because we are the first. The more terrifying possibility is that the great filter lies in our future. Every technological civilization, upon reaching a stage similar to ours, inevitably discovers or creates the very thing that destroys it. This could be the invention of a technology we cannot control, like a runaway artificial intelligence that sees its creators as a threat. It could be the unleashing of engineered pathogens in a world of global travel. It could be the ancient human folly of war, now amplified with nuclear or other apocalyptic weapons. Or it could be something we have not even conceived of yet, a silent, cosmic reset button that periodically cleanses the galaxy of intelligent life. We are racing forward with our technology, building global networks and probing the foundations of biology and physics, without knowing if we are building our own tombstone. The silence from the stars may not be a sign of our rarity, but a warning from an empty graveyard. Are we, right now, approaching the very filter that has left the universe so quiet? Our own ambition may become our greatest obstacle in the final frontier. Beyond the natural perils of radiation and debris, we are rapidly creating a new set of dangers born from competition and commerce. This 20th threat is the toxic combination of resource depletion and orbital congestion, a human-made crisis unfolding just overhead. The most immediate battleground is not a planet, but a line in the sky 36,000 kilometers above the equator, the geostationary orbit. Here, a satellite's speed matches the Earth's rotation, allowing it to remain fixed over a single spot on the planet. This makes it incredibly valuable for communications, weather monitoring, and surveillance. But this prime orbital real estate is finite. There are only so many slots available before signals from different satellites begin to interfere with one another. We are already seeing a territorial rush for these positions, a high-stakes game of cosmic musical chairs where the major spacefaring nations and corporations are scrambling to claim their place. The potential for disputes is immense. What happens when two countries demand the same orbital slot? The arguments could escalate from diplomatic friction into something far more sinister. The temptation for sabotage becomes a real threat. A rival nation or company could covertly maneuver a small, untraceable vehicle to collide with a competitor's billion-dollar satellite, disguising the attack as just another piece of space junk. Such an act would not only destroy a key asset, but would also generate a new cloud of lethal debris, triggering the very Kessler Syndrome cascade we fear. This is the path to warfare in space, where battles are fought silently with kinetic impacts and electronic jamming, raining destruction down on the global infrastructure we all depend on. And the resource rush will not stop in orbit. The next gold rush is aimed at the asteroids and the moon itself. These celestial bodies are treasure troves of precious metals, rare earth elements essential for our electronics, and water ice. Water is the oil of space, not just for drinking, but because it can be split into hydrogen and oxygen, the fundamental components of rocket fuel. The company or nation that masters the art of mining water from a lunar crater or a nearby asteroid will effectively control the gas stations of the solar system, holding the keys to deep space travel and amassing incredible economic and military power. This creates a volatile geopolitical landscape. Will we see a new era of corporate colonialism in space, with private entities claiming entire asteroids as their property? How will international law, which currently states that no nation can claim sovereignty in space, handle a mining corporation that establishes a permanent, resource-rich outpost on the moon? The potential for conflict is written into this future. A clash over a particularly rich platinum asteroid could spark a confrontation, with spacecraft being used not just for mining, but as weapons. We risk projecting our oldest, most destructive instincts onto the greatest canvas we have ever known, turning the promise of the final frontier into just another arena for war and greed. The silence of space could soon be broken by the sounds of our own discord. The very engines that promise to carry us to the stars could become the most devastating weapons we have ever created. Pushing beyond the slow, chemical rockets of today requires harnessing forces of almost unimaginable power, and a single failure would not just doom a mission. It could poison the space around our planet for generations. Consider the concept of nuclear thermal propulsion. This is not a reactor generating electricity, but one used to superheat a propellant like liquid hydrogen to staggering temperatures, creating thrust far more efficient than traditional rockets. The danger is not a nuclear explosion. but the catastrophic dispersal of radioactive material. If a spacecraft using such an engine suffered a launch failure or a violent collision in orbit, it would shatter its reactor core, scattering highly enriched uranium or other fission products across a wide swath of the orbital environment. This would create a radioactive debris field, an invisible cloud of poison that would render entire orbital lanes unusable and pose a lethal hazard to any satellite or crewed vehicle passing through it. We would be polluting our celestial doorstep with a long-lasting, artificial radiation belt of our own making. This risk pales in comparison to the theoretical extremes of antimatter propulsion. Antimatter is the ultimate fuel, the mirror image of normal matter. When the two meet, they annihilate each other completely in a flash of pure energy, a conversion process 100% efficient. The energy released from annihilating a single gram of antimatter would be equivalent to the bomb dropped on Hiroshima. To power an interstellar voyage, a ship would need to carry kilograms of this substance. The engineering challenge is containing it. Antimatter cannot touch any physical container made of normal matter, so it must be suspended by immensely powerful magnetic fields in a perfect vacuum. A single power fluctuation, a microscopic fault in the magnetic bottle, or an impact from a piece of space debris would cause an instantaneous loss of containment. The resulting matter-antimatter annihilation would be an explosion of unprecedented scale, potentially vaporizing the entire spacecraft and everything around it in a flash of gamma rays and particle shrapnel. We are talking about a detonation that could, in a worst-case scenario, eclipse the combined yield of every nuclear weapon ever built by humanity. This is the terrifying paradox of our ambition. To reach beyond our cradle, we must learn to control a star's fury within a metal bottle, knowing that one mistake could mean we never leave home again. That profound silence from the cosmos is not just empty, it is profoundly unsettling. Where are all the other civilizations we expected to find? This question is the heart of the Fermi paradox, and it points to our 19th hidden danger, a threat that is not a physical force but a philosophical and existential one. The universe is ancient and vast, with billions of planets that could support life. The math suggests the galaxy should be teeming with intelligent species, their radio signals and megastructures evident across the light years. Yet when we listen, we hear only silence. This great silence implies something is terribly wrong. One terrifying explanation is the concept of a great filter. This is a hypothetical barrier, a challenge or a developmental stage so difficult that virtually no civilization in the universe can survive it. The filter acts as a cosmic sieve, wiping out intelligent life before it can become a multi-planet, star-faring species. The chilling question for us is the location of this filter. Is it in our past, perhaps the emergence of life itself, or the jump from single cell to complex multicellular organisms, was the nearly impossible step? If that is true, then we are the rare, lucky ones who made it through, and the galaxy is empty because we are the first. The more terrifying possibility is that the great filter lies in our future. Every technological civilization, upon reaching a stage similar to ours, inevitably discovers or creates the very thing that destroys it. This could be the invention of a technology we cannot control, like a runaway artificial intelligence that sees its creators as a threat. It could be the unleashing of engineered pathogens in a world of global travel. It could be the ancient human folly of war, now amplified with nuclear or other apocalyptic weapons. Or it could be something we have not even conceived of yet, a silent, cosmic reset button that periodically cleanses the galaxy of intelligent life. We are racing forward with our technology, building global networks and probing the foundations of biology and physics, without knowing if we are building our own tombstone. The silence from the stars may not be a sign of our rarity, but a warning from an empty graveyard. Are we, right now, approaching the very filter that has left the universe so quiet? Our own ambition may become our greatest obstacle in the final frontier. Beyond the natural perils of radiation and debris, we are rapidly creating a new set of dangers born from competition and commerce. This 20th threat is the toxic combination of resource depletion and orbital congestion, a human-made crisis unfolding just overhead. The most immediate battleground is not a planet, but a line in the sky 36,000 kilometers above the equator, the geostationary orbit. Here, a satellite's speed matches the Earth's rotation, allowing it to remain fixed over a single spot on the planet. This makes it incredibly valuable for communications, weather monitoring, and surveillance. But this prime orbital real estate is finite. There are only so many slots available before signals from different satellites begin to interfere with one another. We are already seeing a territorial rush for these positions, a high-stakes game of cosmic musical chairs where the major space-faring nations and corporations are scrambling to claim their place. The potential for disputes is immense. What happens when two countries demand the same orbital slot? The arguments could escalate from diplomatic friction into something far more sinister. The temptation for sabotage becomes a real threat. A rival nation or company could covertly maneuver a small, untraceable vehicle to collide with a competitor's billion-dollar satellite, disguising the attack as just another piece of space junk. Such an act would not only destroy a key asset, but would also generate a new cloud of lethal debris, triggering the very Kessler Syndrome cascade we fear. This is the path to warfare in space, where battles are fought silently with kinetic impacts and electronic jamming, raining destruction down on the global infrastructure we all depend on. And the resource rush will not stop in orbit. The next gold rush is aimed at the asteroids and the moon itself. These celestial bodies are treasure troves of precious metals, rare earth elements essential for our electronics, and water ice. Water is the oil of space, not just for drinking, but because it can be split into hydrogen and oxygen, the fundamental components of rocket fuel. The company or nation that masters the art of mining water from a lunar crater or a nearby asteroid will effectively control the gas stations of the solar system, holding the keys to deep space travel and amassing incredible economic and military power. This creates a volatile geopolitical landscape. Will we see a new era of corporate colonialism in space, with private entities claiming entire asteroids as their property? How will international law, which currently states that no nation can claim sovereignty in space, handle a mining corporation that establishes a permanent, resource-rich outpost on the moon? The potential for conflict is written into this future. A clash over a particularly rich platinum asteroid could spark a confrontation, with spacecraft being used not just for mining, but as weapons. We risk projecting our oldest, most destructive instincts onto the greatest canvas we have ever known, turning the promise of the final frontier into just another arena for war and greed. The silence of space could soon be broken by the sounds of our own discord. The very engines that promise to carry us to the stars could become the most devastating weapons we have ever created. Pushing beyond the slow, chemical rockets of today requires harnessing forces of almost unimaginable power, and a single failure would not just doom a mission, it could poison the space around our planet for generations. Consider the concept of nuclear thermal propulsion. This is not a reactor generating electricity, but one used to superheat a propellant like liquid hydrogen to staggering temperatures, creating thrust far more efficient than traditional rockets. The danger is not a nuclear explosion, but the catastrophic dispersal of radioactive material. If a spacecraft using such an engine suffered a launch failure or a violent collision in orbit, it would shatter its reactor core, scattering highly enriched uranium or other fission products across a wide swath of the orbital environment. This would create a radioactive debris field, an invisible cloud of poison that would render entire orbital lanes unusable and pose a lethal hazard to any satellite or crewed vehicle passing through it. We would be polluting our celestial doorstep with a long-lasting, artificial radiation belt of our own making. This risk pales in comparison to the theoretical extremes of antimatter propulsion. Antimatter is the ultimate fuel, the mirror image of normal matter. When the two meet, they annihilate each other completely in a flash of pure energy, a conversion process 100% efficient. The energy released from annihilating a single gram of antimatter would be equivalent to the bomb dropped on Hiroshima. To power an interstellar voyage, a ship would need to carry kilograms of this substance. The engineering challenge is containing it. Antimatter cannot touch any physical container made of normal matter, so it must be suspended by immensely powerful magnetic fields in a perfect vacuum. A single power fluctuation, a microscopic fault in the magnetic bottle, or an impact from a piece of space debris would cause an instantaneous loss of containment. The resulting matter-antimatter annihilation would be an explosion of unprecedented scale, potentially vaporizing the entire spacecraft and everything around it in a flash of gamma rays and particle shrapnel. We are talking about a detonation that could, in a worst-case scenario, eclipse the combined yield of every nuclear weapon ever built by humanity. This is the terrifying paradox of our ambition. To reach beyond our cradle, we must learn to control a star's fury within a metal bottle, knowing that one mistake could mean we never leave home again. Even if we master the physics, our own minds might be the final frontier we cannot conquer. Gazing into the cosmic ocean can shatter a person's sense of reality, triggering a psychological danger as vast as space itself. This is the 22nd peril, a profound existential dread born from cosmic awe. We have all seen the breathtaking photographs of Earth from orbit, a fragile blue marble against the endless black. For astronauts, this view often triggers a powerful cognitive shift called the overview effect, a feeling of universal connection and the utter insignificance of human borders and conflicts. But this same perspective has a dark and terrifying flip side. When you stare into that abyss for too long, the feeling of connection can curdle into a crushing sense of isolation. You are not just looking at a beautiful planet. You are looking at every person you have ever known, every memory you have ever cherished, and it is all contained on a single, tiny speck of dust. The sheer, mind-numbing scale of the cosmos can make you feel less like a participant in the universe and more like a forgotten piece of dust on an equally forgotten world. This is not simple homesickness. It is a fundamental crisis of meaning. What is the point of your struggles, your ambitions, your very life, when measured against billions of galaxies, each containing billions of stars? This existential terror becomes a clear and present danger on a multi-generational interstellar voyage. Imagine being born aboard a generation ship, a self-contained world traveling for centuries to a distant star. You will never walk on a planet. You will never feel the wind or see a true sunrise. Your entire universe is a metal hull, and outside your entire existence is a void so immense it defies comprehension. The knowledge that your home, Earth, is not just far away but is receding into mythological history could breed a deep generational despair. For colonists who successfully land on a new world, the psychological challenge is even more intense. They will be completely, irrevocably cut off. A message home would take decades to arrive, and a reply would take decades more. They are on their own forever. The sight of their new sun in the sky, a constant reminder that they are under an alien star, could reinforce a permanent, haunting loneliness. The very stars in their night sky would be unfamiliar constellations, a celestial map that offers no comfort, only a reminder of their exile. The greatest danger for these pioneers may not be radiation or toxic soil, but a quiet, creeping realization of their own cosmic solitude, a psychological void that mirrors the physical one surrounding them. How do you build a society, raise children, and find purpose when you are a tiny flicker of consciousness in an infinite, indifferent night? That profound sense of cosmic solitude is mirrored by a legal void just as vast and unsettling. The rules that govern our world stop at the edge of our atmosphere, creating a 23rd danger that is entirely of our own making, space law, and jurisdictional gaps. The primary framework for this new frontier is the Outer Space Treaty of 1967, a document born from the optimism of the early space age. It establishes noble principles, declaring that space is the province of all humanity and that no nation can claim sovereignty over celestial bodies. But this foundational treaty is dangerously thin on specifics and completely lacks any real enforcement power. It is a constitution for a kingdom with no police, no courts, and no clear way to resolve disputes. Imagine a scenario where one nation, under the guise of scientific research, secretly outfits a satellite with a kinetic weapon. It could maneuver close to another country's crucial military or communications satellite and, with a subtle burst of its thrusters, cause a catastrophic collision. Under the current legal regime, how would you prove hostile intent? Who would hold that nation accountable? The resulting debris cloud would be an act of war disguised as a tragic accident, with no clear path for justice or restitution. The problem extends beyond nations to the burgeoning private sector. A mining corporation establishes the first permanent base on an asteroid rich with platinum. They argue that while they do not claim sovereignty over the asteroid itself, they do claim exclusive mineral rights as the entity that invested in its development. Another company or a rival nation disputes this claim and sends its own spacecraft to mine the same rock. The potential for a standoff or even a violent confrontation millions of miles from Earth is very real. There is no intergalactic sheriff to mediate. An accident only compounds the chaos. A private space tug from one country negligently collides with a crewed spacecraft from another, resulting in the loss of life. Which nation's laws apply? Where would the families of the victims file a lawsuit? The current legal framework offers no clear answers, leaving grieving families in a labyrinth of international courts and conflicting national regulations. This legal gray area is not a mere academic debate. It is a powder keg. A dispute over a lunar mining outpost or a prime orbital slot could easily escalate, dragging terrestrial rivalries into the celestial realm and sparking conflicts that reverberate back on Earth. We are racing to occupy a new frontier without first building the essential foundations of order and justice. How can we hope to peacefully settle the solar system when we have not yet agreed on the most basic rules for living there? The most insidious danger of all may be the one we create for ourselves, the slow erosion of our own vigilance. As rockets launch with increasing frequency and space tourism becomes a reality for the ultra-wealthy, there is a growing risk that we will forget the blood-soaked lessons written in our own history. The immense complexity and peril of spaceflight can begin to feel mundane, a routine commute rather than a voyage into a realm that demands absolute perfection. This creeping complacency is a poison to the culture of safety that astronauts and engineers have painstakingly built over decades. The fire that consumed the Apollo 1 capsule during a ground test in 1967, the heartbreaking disintegration of the Space Shuttle Challenger 73 seconds after launch in 1986, and the loss of Columbia during re-entry in 2003, these are not just historical footnotes. They are stark, permanent monuments to the consequences of cutting corners, of ignoring engineering concerns, and of underestimating the brutal physics of the environment we seek to enter. Each tragedy forced a painful but necessary reckoning, leading to sweeping changes in design, procedure, and a renewed commitment to a safety-first mindset. That mindset is a fragile thing. In a new era driven by corporate competition and aggressive timelines, the pressure to move faster and cheaper is immense. The temptation to streamline safety protocols, to treat a near miss as a success rather than a dire warning, grows stronger. Imagine a future where spaceflight is as common as air travel, and a company, eager to maintain its launch schedule, decides to proceed despite an anomalous sensor reading, dismissing it as a minor glitch. That single decision, born from a complacent belief that the danger has been tamed, could lead to a catastrophe that claims lives and shatters public confidence for a generation. Remembering the fallen is not just about honor, it is about survival. The ghosts of Apollo 1, Challenger, and Columbia must ride on the shoulder of every mission controller, every engineer, and every commercial space CO. Their legacy is a constant, sobering reminder that space will never be safe, that it will only be survived by those who treat it with the utmost respect. As we open the final frontier to commerce and colonization, will we carry the hard-won wisdom of our past with us? Or will we be doomed to repeat its most terrible lessons? Beyond all the dangers we can list and study lies the final, most humbling threat. It is the ultimate unknown, the 25th danger, the peril of what we do not even know we do not know. Our entire understanding of the universe is built upon a foundation of physics that we have tested here on Earth and in our immediate cosmic neighborhood. But what if the deeper reaches of space hold rules we have not yet encountered, forces that do not play by our familiar laws? Consider the possibility of a bizarre quantum effect that only manifests over interstellar distances, a phenomenon that unravels complex molecular structures or scrambles the very bonds holding matter together. A spacecraft venturing into such a region might simply disintegrate into a cloud of disconnected particles, not from any impact or radiation we understand, but from a fundamental property of reality we have yet to discover. Or perhaps the fabric of spacetime itself has hidden textures and flaws, cosmic potholes that could violently tear a ship apart or trap it in a gravitational eddy from which there is no escape. The most unsettling possibility involves dimensions beyond our perception. Our reality has 3 spatial dimensions, but many theoretical physicists posit the existence of many more, dimensions that are curled up and hidden from our senses. What if our voyage through space accidentally intersected with one of these folded dimensions? The interaction could be catastrophic, instantly unmaking the ship and its crew in a way that would be completely incomprehensible to us. We have a long history of stumbling into unforeseen dangers. When the first deep-sea explorers descended into the abyss, they had no concept of the crushing pressures that awaited them. When doctors first began using X-rays, they were blissfully unaware of the cumulative, cancerous damage the radiation would cause. Every new frontier has revealed hazards that were unimaginable from the safety of the shore. The vast, unexplored ocean of space will be no different. The silent, empty void between stars may be whispering secrets about the true nature of reality, secrets that we are not yet equipped to hear. This is not a reason to stop our journey, but a profound argument for proceeding with caution, curiosity, and above all, a deep and abiding humility. The greatest danger may not be the one we can see coming, but the one we cannot even conceive of until it is already upon us. From the silent rain of cosmic radiation to the existential threat of the Great Filter, we have journeyed through a universe that is far from the peaceful void it appears to be. These 25 hidden dangers, from microscopic particles shredding DNA to colossal gamma-ray bursts capable of sterilizing worlds, paint a terrifying yet undeniably fascinating portrait of our cosmic neighborhood. The very hostility of space is what makes it the ultimate frontier. It does not yield its secrets easily, and it demands absolute respect from any who dare to venture out. This knowledge is not meant to frighten us into inaction. It is our greatest shield. Understanding these perils, from the psychological torment of deep space isolation to the legal gray areas we have yet to resolve, is the crucial first step in preparing humanity for its next great chapter. Every danger represents a puzzle to be solved, an engineering challenge to be met, and a reminder of our own fragility and resilience. Our future among the stars depends on our willingness to learn, to adapt, and to proceed with a blend of boldness and caution. So stay curious, support the scientific research and the rigorous safety protocols that will protect the explorers of tomorrow. The journey is only beginning, and it belongs to all of us. Now we want to hear from you. In the comments below, tell us which of these hidden dangers you find the most frightening, or which ones surprised you the most. Your perspective is part of the conversation that will ultimately carry us forward into the great, dark, and beautiful